All right, so we pick up from where we just computed what the tension is in the guide wire. So now we'll end up calculating what the force was at the weld point. So we go back to our free body diagram. We now know what the tension in the guide wire is. It's going to be 264 newtons off at the angle. We know what the downward forces were. We got the tension due to the 10 kilogram mass at 98 newtons. We have the weight of the rod, 32 kilograms times 9.8. And then we have our unknown weld force. We are at equilibrium, so in principle I can choose any coordinate system I want. It is convenient for me to end up picking one though, since I know a lot about the horizontal and vertical directions, to end up choosing horizontal and vertical as being my two coordinates. So if we look in the horizontal direction, my net force will equal the mass of my system times my acceleration, which is 0, so I don't have to worry about what the mass of my system is. In terms of my horizontal ones, I have only two forces that have a horizontal component. I have the tension in the guide wire, and I have my weld force. So my component of my tension is going to be minus 264 times the cosine of 52 degrees, then plus whatever my x component of my weld force is. So I calculate from there that my x component of my weld force is 163 positive newtons. So as I already had said before, that the camera reverses directions. So that away is I know I had a component for my weld force, so I expected it to be positive. My y direction, I'd drawn it as being probably positive, but I wasn't sure. In the y direction, I have all four forces have a component. So my guide wire is providing an upward force, a support force of 264 times the sine of 52, then minus my weight of the 32 kilograms weight, minus my 10 kilogram weight, then plus my y component of my weld force. I go through and do the arithmetic. My weld force y component will be 204 newtons. So the magnitude of the force at the weld, then I use the Pythagorean theorem and I find 261 newtons is the magnitude. And I have to pick an angle here. I've got my other angles relative to horizontal, so I'll choose this one also relative to horizontal. And I end up finding that my angle is 51.4 degrees above horizontal, and that turns out very strangely to be close to my tension direction. That is totally random. That's not generally going to be the case. But the force at the weld is then going to be 261 newtons, and it is at 51.4 degrees above horizontal. All right. Then our last category of stuff we're going to talk about will be levers. All right, so if we end up having that, remember what normal force does. Normal force is a force between two solid objects that prevents one of them from passing through the other. So if I end up having a solid at some location, then it will prevent the other solid from passing through. So my hand can't pass through my finger, but there's no restriction that this provides anywhere where there isn't any mass over here. So it doesn't prevent me from going that way, it doesn't prevent me from going that way. So this ends up being a point at which I get a natural rotation perpendicular to that spot. And we end up calling a solid object that we connect at something that is at some angle there. Relative to it, we end up calling this thing a fulcrum. And that our principle in terms of how we're going to use this, that when you use a lever, the assumption we're going to end up making is that it's going to end up moving, but not really rapidly. So in this situation, although your angular acceleration, you started from rest and it would start to do this, the angular acceleration is not zero, but our assumption is that it's small enough that we can ignore it. So, and especially in some cases where, if we're going to give an example in a minute where we end up popping a paint can. So initially, if it's zero, then as long as it still is at rest, as long as it's still in equilibrium, then it certainly is going to have no angular acceleration. But in general, when we're talking about a lever, we're going to be assuming that your angular acceleration, like I said, is small enough, even though it's not zero. The angular acceleration is small enough that we can ignore it, in which case we can end up saying that it is approximately at equilibrium, even if it's not perfectly so. So let's give an example. We suppose we've got 125 gram screwdriver. We end up having a paint can on here. So this is wedged under by a half a centimeter under under here. So the lid is on this side, the back of the lid. And at that point, a half centimeter there, that's where it's on the side of the paint can. So the side of the paint can is acting as my fulcrum. So I end up providing a force perpendicular to that of 80 newtons. And we'll say the screwdriver has a mass of 125 grams, which is reasonable numbers for both of those. We want to end up finding the force acting on the paint can lid, because in this situation what you're trying to do is to pop it off, so you need to have a lot of force in order to be able to cause it to move. So the diagram is, it's okay-ish. Hopefully you can end up understanding it from the geometry I do with my hands if you don't understand the picture. The force that is provided by the screwdriver on the paint can. So the screwdriver is a piece of solid, the paint can is a piece of solid. So it's normal force. So the paint can prevents the piece of the screwdriver from going through it, because if it didn't, then it wouldn't work. Right? It would pop up. So it wouldn't pop the paint can. It would just cause the screwdriver to pop out without doing anything. So it's normal force, so it is perpendicular. The force that you applied was perpendicular. So we end up finding the net torque at fulcrum. So the torque from the 80 newtons that you apply pushing down this way is going to end up being your lever arm. So the length of the screwdriver is 14 centimeters. Half a centimeter was to the fulcrum on that side, so the other 13.5 centimeters, that's your lever arm. And in fact, this is lever, is where the word lever arm comes from. Multiplied by the force, which I gave as 80 newtons, which again is a reasonable force that you can make. That, and times the sine of the angle. We applied it perpendicular to the screwdriver, which is also typically the way you'll do it. If you grab a screwdriver and you pull it that way, if you think about which direction you're tugging it, it will be perpendicular typically. So that's, again, not an unreasonable assumption. So we end up getting 10.8 Newton meters. We'll pick my positive direction to end up being out of the screen. So, and do your right hand rule, that is positive. So we get a positive 10.8 Newton meters. Then we end up finding the torque due to the screwdriver. So the screwdriver has its weight. Weight will be at the center of mass. And we're going to end up making a slight assumption here, and we'll end up seeing later on that if it wasn't perfectly right, it will be a small error. We're going to end up assuming that the midpoint of the screwdriver is its center of mass. Now, a screwdriver is not symmetric, so it's not going to be quite perfectly that way. So you have the handle on one side, but then you have a large wedge on the other side. It's probably not going to be exactly at the center, but we'll make that assumption. At least it should be close. So then to end up finding your lever arm, the weight is at the center. The fulcrum is 0.5 centimeters from the edge, so it's the distance, say, from the bottom to the midpoint. Subtract the 0.5 centimeters. So the difference there is the half the length, which was 7 centimeters minus half a centimeter. So you'll take that multiplied by the weight of the screwdriver, which is 0.125 kilograms times 9.8. Then, in order to find the angle, the force is straight down. You're given that the angle relative to vertical was 65 degrees. So this is vertical. Angle to vertical is angle to vertical 65 degrees. I'm so sorry. Again, it's the thing with the camera reverses it. The angle is 65 degrees. So we multiply those together and you get 0.072 Newton meters. So notice that number is much, 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 much smaller than the 10.8, which is one of the reasons why, again, if we didn't get that exactly right, it really is not going to make much difference at all. So finally, before the paint can lid is moved, it is at equilibrium because nothing is rotating yet. There's no motion yet. So my angular acceleration is 0 at that instant, and even afterward, it's going to be close. So then my net torque is my positive 10.8 from the 80 Newton force you provide, the positive 0.072 Newton meters from the weight of the screwdriver, then the amount of torque due to the lid that has to add up to 0. So the torque at the lid has to be negative 10.9 Newton meters. The magnitude is your lever arm, and of course it's acting at 0.5 centimeters from the end of the screwdriver, so that's your lever arm, times the force acting on the lid times the sine of the angle, which we said was 90 degrees. So that ends up giving you 0.5 centimeters, 0.005 meters times the lid force. So then that was the magnitude, so we set that equal to the magnitude of the torque, which is 10.9 centimeters. So we solve for the force of the lid is 2,180 newtons. So in this situation, notice that, again, the torque from the screwdriver is much, much smaller, from the weight of the screwdriver is much smaller than the torque from the applied force. This often, but isn't necessarily always true, but it's often true. And whenever that is the case, and whenever the angles are 90 degrees, as they were here, we can end up simplifying the calculations by a lot. So the torque will end up being the first lever arm times the force that's applied times the sine of the angle, then minus the lever arm times the force times the sine of 90 degrees from the other one will equal 0. And when you clean that up, you get the lever arm times the force on one side is equal to the lever arm times the force on the other side, which is the formula for levers that you would have learned in grade school. So again, that's where that actually comes from. That's why it works. And as long as the object, the lever, has a really small torque compared with the other torques, then that's a legitimate calculation to do. But again, bear in mind that it can be incomplete, and this gives you a more complete understanding of how levers work. All right, so that concludes really the new material for this course. What we're going to do next, I'm going to end up putting in a discussion piece for the group quiz stuff I'm going to have on here. I also will have one where I'm going to solicit questions that you would have over next week's lab final exam. And I'll end up trying to address questions that you have on that in next week's lecture bit, because there's really no more lab to do after the one that you're going to do yesterday. I recorded this on Tuesday, so for me it'd be tomorrow, but for you it's yesterday. So So that will be, and if you have any questions that you want to look at on that, please put those in. In terms of general topics, just looking all the way back, we have lab safety stuff, so make sure that you go back and you look at that and what we talked about in the lab and additional things with that. You should know how motion detectors work. We did a hell of a lot of motion detector stuff. So, you should know positive directions, you should know accelerations and how acceleration and velocity work, which is positive, when it's negative, relative signs of velocity and acceleration, what all that means, all that sort of stuff. You should know how to do 1D kinematics. So, big four stuff, that's legit. You should know force acceleration relationship. We did some stuff with that. You should know information about how springs work. You should know information about see. You should know accuracy and precision. Let's see. I think that's. You should know the conservation of momentum stuff. So we had the lab on that. So know how to understand how collisions work, all that sort of stuff. And like I said, if you have any questions, you want to go over examples, you want to whatever like that, let me know. And as of right now, I'm working on the assumption we will have that lab final, and it will be. I will try to put it on Georgia View, and I'll see how that works. And if that happens, then it will end up being on Georgia View, and you would end up taking it during the time period that's allotted. I will not restrict you from using your lab materials that you had. You can end up using whatever. You can use your textbook, your lecture notes, whatever you want. I normally don't, but again, this stuff is weird, that we're dealing with. So I'm hoping that ends up helping you out a little bit, and so that's really what's going on.